we are gathered here today. No, not really. Okay, so we have a very distinguished guest with us, Eli Ben Sasson. I may be mispronouncing that. He will correct me. Who is a co-inventor of ZCash and founding scientist of the ZCash company, and the chief scientist and co-founder of StarkWare. So, who here has heard of the concept of ZK snarks? Okay, great. And how about ZK Starks? All right. All right. Well, interesting. Okay, so everybody who hadn't heard of Starks is going to hear about them today. Eli, do you want to quickly introduce yourself?
Yeah. So first of all, thanks so much for having me here. Great fan of Coinbase, and so I started off as a researcher in theoretical computer science, and then I slowly moved more and more into the practical world, and then I think the world of cryptocurrencies discovered me. Or called on it, and then I sort of got into cryptocurrencies first with Zcash and the Zero Cash paper that I was a co-author of, and later on and more recently with StarkWare that I hope to tell you a little bit about, and ZK Starks, and yeah, so now I'm full-time at our startup.
Great. Victoria, can you just get those folks to quiet down over there? Thank you. So that's awesome. And, just like before we jump into, StarkWare and Starks and all the details, could you share your aha moment? Like, when did you get into blockchain? When did you realize this was actually going to be a big thing and so on?
My aha moment was very distinctive. It was in the San Jose Bitcoin 2013 conference. I was giving a series of talks about my research, which was practical implementations of things called probabilistically checkable proofs, and I also asked to speak at the conference there, and I think it was Gavin Andreessen and Greg Maxwell back in the day were supportive of it, and it was by far the most electrifying conference I ever attended, and it was the point where I realized that the technologies that we're developing, practical implementations of proof systems, are really, really important for decentralized cryptocurrencies. Mm-hmm. And my life changed since that occasion.
Amazing. Yeah, in many ways, what's happening to crypto is sort of what happened to AI and ML, where it was an academic discipline for a long time and then amazingly commercially important very quickly. Mm-hmm. So then, speaking of commercial importance, why don't we talk about, kind of StarkWare at a high level, if you want to talk about like what the company does. For example, it's not doing an ICO.
Right, so it's not doing an ICO, and we're not competing to be the next internet money. We're developing this technology that I'll tell you a little bit about later on, ZK Starks, which is similar in a certain way to the snarks of Zcash, but in many ways it's a little bit better, especially for scalability. It has no trusted setup. So we are developing this technology and deploying it. Our first product, our first deployment is going to be released in 2 months. It's going to be a scalability solution for decentralized exchanges. And we are a startup located in Israel. We have right now 20 folks. Almost all of them are engineers, who are deeply versed in math and in programming as well. And we're developing Starks for deployment.
Amazing. So just to show of hands here, who here has heard of zero knowledge proofs? Okay. Who here can explain what a zero knowledge proof is? One little wavy hand. Okay, great. So why don't we introduce the room to zero knowledge proofs just in general, maybe the grocery receipt example or however you want to do.
Okay, so zero knowledge proof is this marvelous concept that was introduced in a fundamental academic paper 34 years ago or so by Shafi Goldwasser, Silvio Micali, and Charlie Rakoff. They received many awards for this, including the Turing Award to Micali and Goldwasser. So a zero knowledge proof is, first of all, it's a kind of a proof. So it's something that you can attach to a statement, and you can easily attach or efficiently attach it to true statements, but it's almost impossible, or it's intractable to attach such a proof to an incorrect statement, because it will be seen that it's that something there is amiss or wrong. So first of all, it's a proof, but the proof itself is a bunch of information. And a zero knowledge proof has the property that the information contained in the proof itself does not reveal anything but for a single bit, which is that the statement is correct. So for instance, to give a concrete example, if I would generate a zero knowledge proof, for instance, that I hold 3 Bitcoins in the latest UTXO set, when you see that proof, you will learn nothing but for the fact that I indeed hold 3 Bitcoins in the latest UTXO set. In particular, you won't know which Bitcoins I hold. So it's a proof that reveals no information but for the correctness of the statement.
Right. And so there's a useful non-technical analogy with the green and red balls that maybe helps people get a sense of the flavor of how a zero knowledge proof could actually happen. Do you want to explain?
Yeah, so the example, first of all, zero knowledge proofs are there to prevent leakage of information in the case of some asymmetry in information. So if we all know a certain fact, then you don't need zero knowledge to prevent its leakage. But suppose you have passwords or some private information you want to protect from a party that doesn't know it, then a zero knowledge proof is handy. So the example goes like this. Suppose a person is colorblind and I'm not colorblind, okay? And I want to prove, so I have there's some asymmetry here in the situation, right? I have some knowledge or some ability that the other party doesn't have, right? I am not colorblind. And I want to convince the other party that I have this extra fact that, right? I am not colorblind. So how can I convince the other party that I'm not colorblind without revealing any other information but for that? So the other party holds 2 balls, one is red and one is green, and I want to convince this other party that I can distinguish between these 2 balls, right? But I don't want to give this other party any information about which ball is red and which is green. So the way I'm going to ask this other person to put the balls behind their hand, behind their back, and then either switch them or not switch them, and I'll be able to tell the other party whether a switch occurred or not, right? And if I know, right, this person presents the balls, I can see which is red and which is green, and then if a switch occurs and I am not colorblind, I can say, oh, a switch occurred, right? Now, when I give this information, I reveal nothing but the fact that I know to distinguish between a switch and a non-switch, but I'm not revealing any information about which ball is red and which ball is green. So this is some example of a zero knowledge proof. It prevents leakage of information about which of the 2 balls is red or green, while still convincing the other party that I hold this ability. So that's an example of a zero knowledge proof.
Right, and the key to that is it's probabilistic, right? In the sense of, you might guess it correctly the first time, but then if you iterate that 500 times, and every time the person with green and red balls does a switch or a non-switch behind their back, you're able to correctly guess if a switch or a non-switch happened, then you've got a 1/2 to the 500th chance of getting it correct. So it's a probabilistic convergence in that case.
Precisely, right? and bounding the probability of error is a significant mathematical challenge that also has implications on the construction of these proofs.
Yep, great. So this, by the way, is also similar to like mining. Bitcoin mining finality is kind of probabilistic. After like 6 blocks, the probability reduces. So similar in that sense. So how about the aspects of ZK Starks that are notable is they help with blockchain scalability, they help with transparency, they help with privacy, and they're also very efficient to compute. Why don't we go kind of one at a time? First on the transparency point, because that's one of the biggest differences from so-called ZK Snarks.
Yeah, so the T in Stark stands for transparency, which means no trusted setup. It means if you want to use it, you want someone to prove to you that a statement is correct, you don't need to run through any ceremony for setting up parameters. Basically, the system, you just, the prover sends a proof and you check that proof. So that's the T in the word Stark, and it's very important transparency for a lot of reasons, right? Dealing with the trusted setup is a big issue, and you would like to remove it. So Starks do precisely that.
So just to also give a little more context on the whole trusted setup problem, at the time when Zcash was founded, and when the chain was about to be begun, there's a process that generates a byproduct, so-called toxic waste, which could be used to silently print new ZEC, new units of the currency. And so you just have to sort of trust the founders that they did not keep that private key, which is a backdoor to be able to privately mint more ZEC. The way the Zcash team tried to obviate that concern is they had a bunch of observers to show that they had destroyed it and so on and so forth. But like that's like suboptimal in like a trustless blockchain to know that there might be a small probability that someone could mint a bunch of that ZEC. So the ZK Starks are trying to solve that problem so that when the blockchain is set up, you don't think somebody might, with some probability, have a backdoor of some kind. I don't believe Zcash does have that backdoor, but just some.
Neither do I.
Yeah. So okay, great. So so we got through kind of zero knowledge at a high level and the green red ball example. I'll paste a link into the channel afterwards so folks can take a look at that. It gives at least an intuition for it. We got through Starks versus Snarks. Snarks have this trusted setup where someone could backdoor the chain potentially. Starks do not have that. They've got the transparency. Why don't we talk about the so privacy is something which is sort of implicit. Zcash kind of pioneered this concept of you could argue, Monero and others did as well, but of using zero knowledge proofs, at least Zcash pioneered that concept. You want to talk about the privacy aspects?
Yeah, of ZK Starks. So ZK Starks, so the ZK stands for zero knowledge, and they also deliver the same privacy guarantees that you get from a ZK Snark. You could construct zero knowledge proofs with them, so they could replace someday, for instance, the Snarks in Zcash without any need for a trusted setup, which would be very useful, for instance, for rolling out new, new forms of the circuit without sort of needing to run the ceremony for the trusted setup time and again. So it could be very useful for that. Another place where no trusted setup is really important with zero knowledge is if you would like some big central party to deploy a system, for instance, the government, where it makes assertions and then it convinces the citizens or the public that these assertions are correct. So if you have a trusted setup that's needed for this system, the citizens might worry whether the government hasn't really, messed around there and hold some backdoor. With ZK Starks, this could never happen because there is no backdoor that anyone is aware of, and that's a very big difference.
Awesome. Yeah. So one way I think about it is, problem. You have things that are in the blockchain, so blockchain snooping. Solution, zero knowledge, ZK Snarks and Starks. Problem, trusted setup for Zcash. Solution, ZK Starks. Another problem is a whole 1MB thing, right? So who here remembers the whole 1MB block size debacle? Nobody? Oh, come on. Everybody remembers the Bitcoin Cash. All right. Wow. Okay. I feel really old now. The gray is coming in. So, a year and a half ago, there was a huge fight between Bitcoin and Bitcoin Cash over 1 megabyte as whether that was the right amount, of data to include in a block. And fundamentally, that's an argument over scarcity and scalability. And ZK Starks have something to say about that as well in terms of scalability.
Yeah, definitely. The main thing that StarkWare wants to use first is the scalability of ZK Starks. The S in the Stark actually stands for scalability, which means that the time needed to generate a proof is nearly linear in the size of the computation or the amount of throughput, while at the same time, the time needed to verify a proof is exponentially smaller than the computation. So let me give you a concrete example, which is actually this alpha product that we're going to put out in 2 months on Ethereum. So you're probably familiar with decentralized exchanges in which all of the settlement occurs on the main chain. So each trade, when it settles, must generate some transaction on the main chain of Ethereum. I'm talking now about DEXs over Ethereum. DEX is decentralized exchange. So in a decentralized exchange, each trade leads to a settlement that must go on chain. And currently, each settlement costs about between 100 to 200,000 gas, which means that there's a limit on the number of trades that could settle on Ethereum. If you do the math, it's about at most 3 transactions per second, even if all of Ethereum's throughput goes to settlement of decentralized exchange trades. Okay, so what we showed yesterday in our demo at the SBC conference was that we can generate a proof for settling 10,000 transactions with gas cost that is amortized 800 gas per trade, as opposed to 200K gas per trade. And the amount of gas required to verify this proof on chain is less than a single block. So in a single block of Ethereum, in 2 months, we'll have a solution that could, in a single block of Ethereum, settle more than 10,000 trades of a decentralized exchange. And I mean, we hope this might also interest Coinbase, at least through Paradix and so on, but we're definitely going to deploy it. We're working with 0x closely, with Warren and others there, and it's in 2 months we'll deploy it.
Awesome. So that's a very powerful thing. Basically Starks is a form of data compression that could get DEXs to scale, which is obviously of interest to everybody here. Okay. So now there's another technology out there, bulletproofs, which represent an improvement over ZK snarks in a different way. And maybe you can kind of talk about like where they fit on a kind of pre-optimal trade-off.
Yeah, so bulletproofs is this amazing new technology by Dan Bonnet, Benedict Boons, and a few others at Stanford and other places. And it is also a privacy solution like ZK snarks. Its main advantage over ZK snarks is that it has no trusted setup. So it is transparent. Transparent means no trusted setup, just like Starks. So bulletproofs and Starks have no trusted setup. Snarks have the shortest proof length, and verification time is small once you ran the trusted setup. Bulletproofs have factor of 10 larger size proof, about in the 1 to 2 kilobytes, and our ZK Starks are another 1 order of magnitude larger than bulletproofs for a single shielded transaction, around 20 to 30 kilobytes. The main advantage of Starks over bulletproof is that you have this scalability factor. Your verification time is much, much smaller than the time needed to run the computation. Bulletproofs are a great privacy solution, but they offer no scalability benefits because the time needed to verify a computation is at least the size of the computation, whereas in a Stark, it's exponentially smaller. So it's really, there are 3 different technologies. Each one is really, really great and has certain advantages and disadvantages. In terms of scalability, Starks are really the ones that outshine the others, and that's why we're going after scalability with them.
Great. Yeah, Monero has recently integrated bulletproof, so that's a chain which is using those. So what kinds of blockchain applications, we mentioned decentralized exchanges, that's going to benefit potentially from Starks. What other kinds of applications do you think are interesting here for Starks?
So yeah, Starks can give you scalability and privacy. We'll first try to use them for scalability. So DEXs are going to be our first thing. Inside DEXs, we're first going to go after the settlement phase, but later on, we're also going to look into other areas of simplifying and making things better in decentralized exchange. Things like the matching algorithms, asserting to the world that these things operate, correctly according to some specification of the DEX. Later on, we can also do things like, preventing front running and things like that in the sort of order book and phase of this thing. So that's all in the world of DEXs. Other areas that could be of interest are things like proofs of solvency. So we wrote a piece about that and posted it on Coin Center's blog series. Exchanges, centralized or decentralized, could prove to each and every single customers of theirs that, first of all, the exchange in total is in the black, and the liabilities to that customer are actually covered inside the computation of all liabilities. And this could be sent, on a monthly basis to each, or a daily basis, to each and every customer of the exchange. So that's a second area that Starks could be used for, and here you also would probably need the privacy, the zero knowledge aspect of it. It's for proofs of solvency. Later on, if we think that for general accountability and auditability of institutions, banks, exchanges, and other financial institutions, it could
stable coins potentially.
What?
Stable coins.
Yep.
Yep.
Definitely. Definitely.
Good. Great. And so why did you decide to found a company around Starks, versus doing something within academia or what have you? How come? Why StarkWare?
Yeah, it's the natural next step. So I've been researching the theory behind Starks since 2001 when I was doing my postdoc at MIT and Harvard. Back then, I was studying things called the probabilistically checkable proof theorem, which is a marvelous theorem that basically underpins everything that StarkWare and other efforts are doing. And then around 2008, I started dabbling in implementing some of these constructions, which our theoretical work made a little bit more efficient. And the next natural thing after deploying, I mean, we published academic papers on Starks, and we published actually an open source MIT license Git repository called libstark that those of you interested are welcome to look at. And the academic effort is really great and gets you so far, but the next natural step is to actually deploy these things in real products and in the real world. And for that, you need a real business. You can't do that really with the resources that you have in academia.
Absolutely, I agree. So, one thing you guys have is actually a very novel potential business model. I know you haven't actually done it yet, but you've talked about it. You want to talk about that?
Yeah, so we started off saying that we're going to explore what we call the T40 model, the tech for token model, which is, it's a little bit like an analog of venture capital. What does venture capital do? It comes at a very early stage to a startup and says, okay, we'll put our funds to work here. In return, we get some fraction of equity in that project, and then we write it out. If it goes up, we profit. Otherwise, we're there with you. So you could think of VT, venture technology, where you come at an early stage, you bring your technology, you invest it, or help it be integrated into a blockchain. In return for some portion of that, be it an ICO or something else, some coins in that thing. And then if based on your added value, the thing succeeds, then you see an upside, and otherwise you write it along with the project. So it's something that we are still open to doing, and we probably will want to do it later on when we help layer one integration of ZK Starks. But for now, we just thought that it will be much quicker and more beneficial to meet the market as soon as possible. That's why we went to first do this, solution of an actual product, which is this DEX scalability engine that I spoke about earlier. But the tech for token model, first of all, I hope to see other, startups that try to do that, as opposed to, a lot of startups in our space, they come and say, we have some really great new technology. So how do we commercialize it? We form a new coin, and we hope that will be internet money. And our starting position was, we have great technology, but we're going to work really, really hard to not try and, be internet money just based on that, but rather to find ways to integrate it into as many cryptocurrencies as we can. And
yeah, I think it's pretty interesting because it's like almost like a venture consulting model. Because normally with consulting, you teach someone to do something and you're billed by the hour, but then you're done. And in this case, you would actually still have upside, from the tokens, which I thought was pretty interesting. Licensing models in the past, sometimes they've worked really well, like the Fraunhofer model for MP3s and so on. And other times, sometimes it's hard to get somebody else to execute on the vision. So I'm cheering for the DEX example, because I think this is good because it's a library that folks can use. So it fits into an existing application better than like a more full-blown thing.
Yep.
So I think that gives pretty good coverage of Starks, and I think Daisy or I will paste in the StarkWare.com URL and the StarkWare.com, right? I think so.
Yeah. And I should mention we're going to start.
.co. Okay.
.co, yeah.
All right. Don't go to StarkWare.com.
Who knows
exactly.
what's there? But I just want to say that we'll be starting very soon, this week or early next week, to start posting blogs that explain, the math behind Starks. I mean, they're academic papers, but something that would sort of bridge the gap. And please follow us, and you'll be able to follow what we're doing there.
Yep. And okay, so then besides Starks, there's a lot of other stuff happening in crypto and blockchain. What else do you find interesting? What are you folks following?
So there's a lot of advanced cryptography that is now starting to be realized in the real world, and a lot of it is happening over blockchains, and it's really interesting. So ZKPs, everyone here probably knows that it's already deployed, but there are other things like secure multi-party computation, which is like the next level beyond zero knowledge proofs. There are things like recursive usage of zero knowledge proofs, things like what the Coda protocol is going to attempt to do for scalability. Fully homomorphic encryption is a little bit further down the road in terms of maturing, but it's also extremely promising. So I think this is like a golden age for theoretical cryptography being deployed in practice, and we're very proud to be part of that, that wave.
Awesome, cool. So then sort of more generally, these are just sort of the kind of advice and experience for folks. So for somebody just starting out in terms of learning about crypto, where would you point them? Maybe Dan Bonnet's class, or where would you have them start?
Yeah, I think Dan Bonnet's class is a really, really good starting point. About blockchains, well, I mean, you guys probably know enough about it, but there's the Princeton course on blockchains. Those are very good starting points for cryptography and blockchains.
Yeah, the Princeton course, I think Arvind Narayanan and
yes.
Felton's course, right?
Exactly.
Yep. So then what about folks who, maybe if they're expert in other areas of computer science, but they're not cryptography experts, like where, they probably also start there. But for folks who are like, maybe, they're not computer scientists and they can't read a textbook, what would you have them look at, if anything?
For blockchains and cryptography, I would still point them to these 2 points.
Sure.
When I talk to my peers in academia who are in either economics or law, I tell a lot of them that they should look into blockchains and start writing their own papers about it, because there's so many open questions there. To my economist friends, I repeatedly say that I'm sure that like 30 years from now, there'll be a bunch of Nobel Prizes in economics being handed out to some people in economics who will figure out what blockchains are, so they better, start running at it. And I just think that it's, decentralized blockchains are transforming and disrupting so many notions in about society and humanity that it's really, really interesting to anyone with an academic and scientific mind in all aspects.
I think it's a great prediction that, the first blockchain Nobel, that probably will happen at some point.
It should go to Satoshi, but
yeah, you're right.
And a Turing Prize, but
Do they award the Turing Prize pseudonymously? I'm not sure about that. The Nobel is not awarded posthumously, but I don't think that they've ever awarded one pseudonymously. Actually,
No.
they did award the Nobel to like the group of climate scientists a while ago. So that's like maybe the closest proxy. Maybe they could do that. Your point on the economy also reminds me that, back in the 90s, there used to be this concept of 6 degrees of separation, sort of this vague concept. And then we got the social network, which made that a computable data structure where you could see who was friends with who and who unfriended who and so on. And the same, I think, we've got the economy, this vague concept, and then we've got the blockchain where every transaction, the history of an economy can be replayed. And so you can actually do like a more data aware economics than you ever could before.
Yeah, it's also, so blockchains have this sort of analogous principle to direct democracy. We call it inclusive accountability, which is anyone with a laptop is invited to verify and account for the integrity of all of the system. And that's a powerful, novel concept that you don't see applied in the conventional world. In the conventional world, we have delegated accountability. We delegate the process of accountability to, lawyers and regulators and auditors. And here, there's a new notion of sort of direct accountability or inclusive accountability. That's extremely powerful, and I hope and think it will, enter other areas of society and governance, and that's really exciting.
That's interesting. It reminds me of the French concept of surveillance, which is like surveillance from below. Like, so watching, elected leaders and keeping them transparent, or, and
yeah, I love that term.
Cool. So just a few more just to wrap up. So what are you reading right now?
So I'm reading now the three-body problem.
Two.
Okay.
That book is awesome. Don't spoil it. Don't spoil it.
No, I haven't gone far enough, and I'm not sure yet. I haven't formed an opinion because I'm in the beginning, but I'm really impressed by the mixing of both the science fiction aspect and sort of the historical reflection on it's on the the communist revolution and its effects in China in the 60s and 50s. I think it's really interesting.
Yeah, I think he might have a claim for being like China's Solzhenitsyn. We'll see what happens. But what's the most powerful piece of feedback you've ever gotten?
The most powerful feedback I got was, of course, from my parents. And I think it is this, this sort of saying that, I try to also tell to my kids. I have 4 of them. So when my parents were angry with me, which happened quite often, they always had a point of saying, even though we're angry with you now, we love you very much. And I think it's a very powerful statement because love is the one power the one most empowering thing out there, and professing it and saying it up front all the time is really, really important for life.
I'm going to use that in all my one-on-ones now. Even though I'm angry with you, I love you very much.
Very important, especially with your kids.
Yes. Okay, anything else we should know? Anything else you want to say?
No, I mean, I really enjoy this. I think these are excellent questions, and thank you for having me here.
Okay, maybe we can have a few questions for the audience for 5 minutes or so.
Thank you, Daisy. Hi, thanks for a great talk. I'm Vlad, and I have a question regarding the proving of the solvency of exchanges. While it's easy to prove a solvency for a crypto-only exchange, I'm wondering if this technology can be applied to analog technologies where you have to also prove you have enough dollars in a bank account. So as opposed to inviting auditors, can you do that with perhaps ZK Starks?
Yeah, so there's the problem of like cryptocurrencies, sort of the input spoofing problem is completely resolved because you can't, it's cryptographically hard to just say, oh, I have a few new dollars. So with analog, it doesn't work as well currently unless the government at some point sort of closes that loophole. For instance, in the digital dollars that it issues, they would be somehow cryptographically signed, and then when you prove, just like with a Bitcoin, if you have it, you have to prove something cryptographic. But short of that, the closest you could come is to this principle of accountability by time and again publishing on some blockchain a commitment to your financial assets at a certain point in time, and later on using a Stark, which by the way is Turing complete, you can do any computation with it, to assert that you complied by a certain computation. So right now you'll be, suppose we start taking the my bank account balances, and on a monthly basis I just take those statements and I put their hash on a blockchain. So I can add some randomness and make it completely privacy preserving. You'll learn nothing about it. Now, if I'm honest, and in 2 years the government comes and says, or someone says, oh, show us that, prove to us that you computed your taxes correctly, so I'll be able to do that honestly and easily with a ZK Stark. Whereas if I was cheating along the way and missing out on some things, it would be harder. So that would be the closest to that. It still doesn't. I could already in advance be starting to cheat. I could start to cheat and not exactly account for all my dollars there and so on. So it's not a perfect solution. Cryptocurrencies are much better in that respect.
Yeah, one other thing that's interesting is there's something called Zipf's law, another thing called Benfords Law. I believe it's Benford, which is the it's kind of the distribution of digits in real accounting data as opposed to synthetic data, and it looks different. So if you combine that with this, you have at least another check in terms of financial statements. Though you'd have to actually be able to pull the underlying financial statement, which was hashed to the blockchain. Any other questions? Yep. Here.
Hi, I'm Kareem. I work on the infra team. This might be a little bit of a dumb question, but why doesn't a password hash count as a ZK Stark? Because if you hash like some data, you've proven that like non-interactively, and I think trustless as well, so it counts as a ZK Stark. Is this just not feasible for things like 10,000 transactions?
So I didn't give the formal definition of a ZK Stark, but you usually want it to apply to a class of very general computations. So there are protocols that prove in zero knowledge various things, like Schnorr protocols, Sigma protocols, and I believe probably, I have to go through the password hash, but that probably could account for some kind of zero knowledge proof for this very simple computation that a pre-image of some computation. But where things like ZK Starks come in really handy is if you want to do a generic computation, let's say on the pre-image of that thing, and say, I know a pre-image that the sum of its digits is 5, and the social security number matches appears in some list, and so on and so forth. Then you need something that's much more advanced than just these simple protocols. And ZK Starks apply to any computation that you could efficiently do. You can do it with you can prove its correctness with a Stark.
Basically, the function itself is a parameter, as opposed to being fixed, I think.
So then how would you, so I guess in the context of like these transactions you want to verify on the blockchain, could you maybe give a rough idea of how would you do that? Is that with like the Merkle tree, or what are you doing there?
Yeah, so, okay, that's a really good question. Let me try to give some intuition on how a Stark works. So for scalability, we would like the verifier to be able to discern between true statements and false statements exponentially faster than it would even take to run the computation. So let me just say again, the verifier needs to verify the correctness of the computation exponentially faster than even running that computation. And that's a very mind-blowing, magical aspect. So how is it done? And let's go first to how to reality. How do advocates in a court of law discern between true and false statements? So suppose, just to take a hypothetical example, suppose a person is accused of theft, and as an alibi he says, I was not in the country on that day. So if that's a true statement, in the questioning, in the examination that comes afterward, that person speaking the truth will easily be able to answer questions like, where's your airfare ticket? What was the weather that day? Did you notice any smell on the street? Okay, whereas a person that is lying and wasn't out of the country that day would have a very hard time reaching a consistent story. Okay, now to computation. We don't have this aspect of reality that there are a lot of consistency checks internal. So what we do is we artificially insert them. We ask the prover to generate an encoding by an error correcting code of the steps of the computation, and thereby create this artificial universe that has a lot of interconsistencies that would all fall in place if it's true, and be inconsistent if the statement is false. Then the prover sends a Merkle root of the commitment to that encoding, to this artificial universe, and then the verifier can easily find out whether it's true or false. That's how a Stark works.
Okay, great. We're going to wrap it up from here. And please join me in giving a thank you to Eli for coming out.
Thank you so much.